Hello everyone, we'll be discussing some numerical problems on sedimentation in this session. Just for a quick recap, we have studied Stokes' law, the basic form of Stokes' law by considering its definition. Velocity, that is terminal velocity of a particle of size d in a liquid of viscosity mu, and gamma w, the unit weight of fluid. Gamma s is unit weight of the particle which is falling down, and the equation is given by phi is equal to d squared by 18 mu into gamma s minus gamma w. Phi is terminal velocity, d is the particle size diameter, mu is the viscosity of the liquid in which it is falling down, gamma s is unit weight of that particle, gamma w is unit weight of the liquid in which the particle is falling down. Now, for Stokes' law, there is a limitation, like lower limit of the particle size is equal to what is the smallest size of the particle that you can adapt. So that is 0.0002, so to say 0.2 microns. That is a limiting size, lower limit size. This smaller particle is limiting to this because if you go down the size of zero point 0.2 microns, there comes what is known as Brownian motion. Because of that, the particle will not be falling only because of this law, but some other forces will be coming into picture. The upper limit for the application of Stokes' law would be 0.2 mm. If the particle size becomes larger, then there will be turbulence involved. Because of that, again, the law may not be properly applicable. So limitation of Stokes' law is one of the major criteria is size of the particle. Minimum size is 0.2 microns, maximum size is 0.2 mm. Okay. Corrections already we have discussed in length. There is a meniscus correction, dispersing agent correction, temperature correction. We have dealt in length about all this. Limitations of hydrometer analysis, sedimentation. There are four important points. Assumption we made is single particle falling down when we proved Stokes' law. But here there will be number of particles which will be falling parallel to each other. Because of that, there will be interference of themselves and also interference of the container wall when the particles are led to fall in water medium. Then particle is single plus it is assumed to be spherical in nature, but actual particles of soil will be not spherical, but they will be flaky and then needle-like. And then gamma s will be known specific gravity of the particle when we prove this, but in actual case when the soil is led to fall, this gamma s may not be same for all the particles, so you will be taking average of the gamma s. Here obviously a single terminal velocity v, because there will be a specific size d in a test or a proof, whereas here there are too many sizes. Because of that, there will be different velocities, so it will be average of all the particles including adsorbed water. Okay, we'll go into the details of the problems. So here there is one. The problem reads this way: 50 grams of oven dried soil passing through 75 microns test sieve size taken in hydrometer analysis. So this I have represented as mass of soil taken for 1000 cc, that is original mass of the soil which is mixed with 1000 cc, that is MD. You will require this information in calculation of percentage finer in the denominator m by v You can just see here 50 by 1000 is put over here, 50 by 1000. So this particular information will be useful in calculating percentage finer. N is a percentage finer. Okay. Now the corrected hydrometer reading in 1000 ml of soil suspension at 2 minutes elapsed time interval was 25. Now time taken here, time taken 2 minutes, but we want in seconds, so it will be 2 into 60, that is 120 seconds. Now this obviously comes over here. While calculating velocity, we calculate it as effective height of fall divided by time. This time is 120 seconds. I've substituted here. Now RH they have given 25, but you know that it is specific gravity of the suspension. So though it is given as 25, it is actually should be taken as 1.025. This 25 stands for 0.025. Similarly, the other values. Now, effective height of fall, the effective depth corresponding to RH 25 is H equal to 12.1 centimeter. Okay. Now taking G equal to 2.7 and mu equal to 1 centipoise, calculate the coordinates of the point on the grain size distribution curve. Now if you remember, grain size distribution curve will have a vertical axis, horizontal axis. Here there will be size of the particle d, whereas here it will be percentage finer. So what is here is percentage finer. Here in this particular discussion, I have represented that as n. Here it is n. So this n is over here, so to say, and then d is represented as d only. So when you have percentage finer and corresponding d, so any point here will have a value of d, a value of percentage finer. So this will be having a d and n as the coordinates. That is what is asked here. Calculate the coordinates of the point on the grain size distribution curve. So grain size distribution curve is a plot percentage finer versus size. So point on that will have coordinates d and n. You have to calculate d and n. That's what is expected. And as you know, n is directly given by this expression WD divided by m by v into 100. What is WD? WD is weight of soil particles finer than size d mm per ml still suspension at the depth of HC at elapsed time of t. That is what is WD means. And then how to calculate WD? There is a formula here. So this formula will help us to calculate WD percentage. Look at this, weight of soil particles finer than size d per ml still suspension at a depth of h. Now what is that expression? RH minus 1 into z divided by g minus 1. RH is the hydrometer reading 1.025 minus 1, g is 2.7 given, it is given 2.7 divided by g minus 1, 2.7 minus 1, that is to say 0.0398 grams. WD is equal to 0.0398 grams. This is the amount of the soil finer than the size d. Now how to work out d? We'll use this equation. This is Stokes law. Phi is equal to d squared by 18 mu gamma s minus gamma w. Now d squared will be equal to 18 mu he divided by gamma s minus gamma w into t. D squared equal to, if we consider this as the equation, obviously I can work out t squared as 18 mu into he divided by gamma s minus gamma w into t. Okay, here I have substituted 18 mu. Mu is given centipoise. Look here, 1 centipoise, 1 divided by 100, so many poise it will be. So 0.01 poise, but we cannot directly substitute in this equation as poise. You have to convert that into Pascal seconds. So 10 poise is 1 pascals. Again you divide by 10, so it becomes 0.001. So I have substituted it as 0.001 Pascal second. That is mu, 18 mu into C, 18 mu into He, effective height of fall. That is 12.1 centimeter. I am using only meters and seconds in Newton. So I have converted that centimeter into meters, 0.121 meters, divided by, we have gamma s minus gamma w. So here this will becomes, look here, gamma s minus gamma w is written as g gamma w. Gamma s is g gamma w, or gs into gamma w minus gamma w. So this is what is that bracket here, but what I have done is g minus 1 is put inside, gamma w is taken outside. So 2.7 minus 1, gamma w is 9810 Newton per meter cube, multiplied by t, 120 seconds. If you simplify, d squared comes out to be so many meter square, that is 1.08833 10 raised to minus 9 meter square. If you take the root on both the sides, d comes out to be 3.29910 10 raised to minus 5 meters. Again multiply by 1000, so that you will be getting it in millimeters. So the size of the particle will be 0.033 mm. Now WD, 0.0398 grams of soil, is finer than 0.033 mm, but this is out of m by v, 50 grams. So that's why percentage final becomes 80%. 80% of the, because this is 0.0398 grams, this is per ml. Look at this expression, per ml. That's why if you want total, you have to multiply by 1000 here. That is to say 39.8 grams. 39.8 grams divided by 50, obviously almost it will be 80%. So that's how to solve the problem. Study the data given. We have used mainly three equations: the V, Stokes law, this WD RH minus 1 into G divided by G minus 1. This gives you weight of the soil particles finer than size D per ml. That's important. It is not just total quantity. It has to be multiplied by 1000. And lastly, N, the percentage finer, is given by this WD divided by M by V into 100. Okay. There is one more problem. A soil sample of particle size ranging from 0.075 mm to 0.003 mm is put on top of the water surface in a tank. Depth of water in the tank is 3 meters. Estimate the time required for the first particle and last entire sample to reach the bottom of the tank. Now what we can assume is there is a container, there is surface of water, you can just see here, and this depth is 3 meters. That is what is given, 3 meters. Now when all these particles are put on this, the first particle will settle down first. The biggest particle will settle down first, 0.075. The last particle will be settling down when all the other particles are settled down. So this will be taking maximum time, this will be taking least time. Right? Estimate the time required for the first particle and also the entire sample. Assume equal to 0.01 poise, G is 2.7. Okay. Now note, mu is absolute viscosity. It is given in poise, but the relation is 10 poise is equal to 1 Pascal second or Newton second per meter square. So because of that, mu has to be substituted as 0.001 as far as Pascal seconds units are concerned. 0.01 poise, so to say 0.00102 exact value Newton second per meter square, or 1.02 into 10 to minus 6 kilo Newton second per meter square. What is given is G. In gamma W we can always assume. Now further, if I want to find first particle to settle has the diameter of 0.075, the velocity v, if I work out with v equal to, what is the equation we have? V is equal to d squared divided by 18 mu. If you remember that equation, 18 mu into bracket gamma s minus gamma w. That is what is the equation. Now after substituting everything, what all you have to substitute? D has to be substituted as 0.075. You can take care of the units, whether you want to put it in millimeters or meters, you take care of. 18 mu. Mu is viscosity. It is put already in maybe Pascal seconds or kilopascals, whatever, kilopascal seconds. And gamma s is they have given G, so you can put it as G minus 1 into gamma W. Right, gamma W I have taken it as 9.8 Newton kilonewton per meter cube. So first particle will get a velocity of 5.104 into 10 to minus 3 meter per second. Now how much is the time taken for 3 meters fall? In a tank of water 3 meter, time taken would be 3 meter divided by all this. That will be giving you around approximately 600 seconds. 60, so 10 minutes, so to say, approximately 10 minutes for the first particle. Now what is the last particle? We have this. So you know where all the changes have to be made in this equation. Resolve the problem. You will get velocity as 8.17 into 10 raised to minus 6 meter per second. Time taken for settling will be 367,197 seconds. Now this is equal to how many days it will be. You can calculate. You can calculate is 367,197 divided by 60. That gives you so many minutes. Divided by 60. This gives you so many hours. Divided by 24. That gives you 4.25 days. So this will be roughly 4.25 days. That is the time taken for the last particle to settle down. So to say, time taken by the whole soil sample to settle down takes 4.25 days, whereas in 10 minutes the first particle settles down. I think with this we'll stop. Thank you.